All right. Today we are going to talk about one of the key topics in Mechanics 2, that is your bending theory. All right. So basically, the bending theory is a culmination, is a combination of the past few topics that you have gone through. Okay. The first one is your shear force bending moment. Shear force bending moment. Okay. Primarily focusing on the bending moment part. Okay. The second is the stress and strain. Okay, stress and strain. Well, for this part, we are focusing more on the strain. The stress. Okay, compression and tension, the kind of stresses. Okay, direct stress and strain. The third one is the last topic, your first and second moment of area. Okay, the first moment of area being to find the center of gravity of a shape. Okay, usually the cross-section area of a beam. Okay, and then the second moment of area is to find I. Okay, second moment of area is basically I, which is the moment of inertia. Okay, like I previously said, it is an indicator of how resistant is your beam to motion. Okay, for this case, how resistant is your beam to bending? All right, and we gave a very simple illustration. If your ruler bends like this, okay, your cross-sectional area of the ruler here is a long rectangle like this, okay, and it is bending about this axis. Okay, it will be much easier than if I rotate 90 degrees perpendicular and try to bend, try to press in this direction. So yeah, I'm expecting this ruler to bend this way, which you realize is very hard, right? Precisely because the I has changed now. Okay, the orientation of the ruler has become vertical, and you are still asking the ruler to bend about this axis. So the I for this case will be higher than the I for this case. Okay, so we will see that in action in this topic lah. All right, and to help you to avoid the situation where you have to find the SFBM all over again, the papers the exam papers will give you this reference table, okay, to immediately find the maximum moment. Okay, so you have to be able to identify what kind of problem is it in the first place. So if the question say it is a simply supported beam, right, with a single load at the center, then it will be at this case lah. Okay, so if this is the case, right, you go down, this will be the highest moment at the at the beam, okay, which is at the center of the beam here. So the highest moment will be the point load force times length of the beam divided by 4. Okay, if it is a UDL across the whole beam simply supported, then it will be the second case law. Then you will just take WL square over 8 as your maximum bending moment. Okay, if it is a cantilever with point load, you can take this W minus this WL as the maximum moment to use in your calculation. If it is a cantilever with UDL, then it will be WL square over 2. Okay, so the W in this case represents the UDL value lah. Okay, and for point load, it will just be the force of the point load. Okay, so this is how you use the bending moment. All right, then the center of gravity, I will show you later why this part is so important. Of course, we have to use it to find our I. Okay, eventually you have to understand, you have to find out what kind of stresses is being experienced in the beam. Okay, in the beam. On top, is it compression tension? Below, is it compression tension? So when we ask this question, we're actually looking for sigma, the stress. What is the stress at the top? What is the stress at the bottom? Okay, so how do you find out? Okay, so today the formula that is the most important one is this one. Sigma is equals to my over I. Okay, sigma is equals to my over I. So you will notice that straight away moment will come in. Okay, this is where you find the maximum moment using the formula table. And then the I is the I that you need to find based on the cross-sectional shape of the beam. Okay, so this is where you have to find the second moment of area, and Y will, the value Y will, I will show you later where to find this. Okay, so eventually you'll be able to find out the stresses at the different location of the beam. Okay, either it's at the top or at the bottom or in the middle. Okay, so that's what this whole topic is about. Okay, so maybe I start off with a very simple diagram. Okay, this one. Okay, so you can see here is a simply supported, okay, single point load at the center. Okay, this is what you should draw as in your free body diagram now. Of course, then you have a reaction at both ends lah. Okay, but okay, what I want to show you is not this. If you imagine the beam, the actual beam itself, okay, is being pressed down at the center here. Okay, the shape will change. Okay, instead of a straight line, right, it is actually a banded line like this. Okay, so it is undergoing this pushing down at the center. And if you zoom in, if you zoom into the thickness of the beam, okay, you can actually draw something like this. Okay, so you will see that at the top it's already being pressed, okay, and the bottom, right, is being actually stretched out in this way. Okay, the top is being pressed, is being compressed in this way, and this is caused by the load. All right, and if I draw it in the three-dimensional figure, okay, it will look something like this. Okay, so the beam is being pressed down at the center. Okay, and because of that, the orientation of the beam changes. Okay, gets warped towards the center at the top, but the below, right, is actually going apart. Okay, so I hope you're able to see this, to see it in a clearer, if I remove the supports, right, it is basically you see this cross-sectional area. If I bend up and down, right, like this, if I make it smile and frown, you realize that the cross-sectional area, right, is actually keep on doing this pattern. Okay, keep on rotating. About where? Okay, about this red line. Okay, so when I bend, when I apply a force at the center downwards, okay, the rectangle is going to do this. Okay, when I apply a force upwards, pushing it up, right, the cross-sectional area is going to do this. Okay, so the whole cross-sectional area is rotating about axis. Okay, and you say that, yeah, it's rotating about axis. And when we bend like this, okay, if you imagine you are the beam, the top will experience a compression. The bottom will be like being pulled apart. Okay, the top is being pushed because the forces push against each other. That is a compression stress. Okay, the bottom is being pulled apart. It is a tension stress. So on top is compression. Below is tension. Okay, of course, if you bend the other way, okay, instead of bending this way, you bend this way, then the story will be different. The top will be pulling apart, right? So the top will be tension, the bottom will be compression. Okay, and yeah, so it's like this lah. So the top tension, bottom compression. If you still can't picture it, imagine the accordion. You know the instrument, musical instrument that is an accordion. The fold actually tells you. You see when the accordion player squeezes like this, you see the folds in the center, right, actually get cramped towards the center, get more cramped. But the below, the folds are actually far further apart. Okay, this means that it's being pulled apart. The top is being pushed together. Okay, so that is what's happening to the beam. Oh. Alright, once we establish this part, I want to show you something. So we have learned that in the stress strain topic, positive stress is tension, right? And negative stress is compression. Okay, so positive stress, okay, tension belongs to the right hand side, because the stress axis, if I plot the axis this way, this is a zero stress value. This right side will be positive stress, okay, and this left side will be all negative stress. All right, and you find out, you see that this one, if the diagram that you usually plot will be against y. Okay, what does y means? Y means the height, the position away, the height basically is the height so bottom to the top. Okay, and at the top, let's say for this case you're experiencing compression, right? So the top stress should be negative, so it should be around here. Okay, the bottom stress which is here should be tension, so it should be positive around here. Okay, then you will ask, then what happens at the middle? Okay, the simple question is, you remember the axis that I draw like this, that the rectangle rotates about this axis, right? This axis is what we call the neutral axis. Okay, so why is it called neutral? Neutral means zero. Okay, this line is where there is no stress. Okay, sigma is equals to 0. So this point, right, sigma equals 0, right, is actually along this line, which is this height. If I'm gonna draw this line across the whole length of the beam, right, it's gonna look like this. Okay, along this line there is no stress. Okay, so here what you would do is, this place with no stress, right, you will set this as the origin here. 0 stress, 0 y. So this is where y is 0. Okay, and as you go up to the top, your y go up to the top, you experience a compression, your sigma is negative. Okay, so at the top, where you are at the top surface, right, let's say this is the surface, this height is the surface, right, I will be at a negative stress. If I go below, bottom, okay, the tension is going to happen, so my stress is going to be positive, right? So at the bottom, the stress is going to be here. Okay, so if this is a regular rectangle, you should have the same height, measuring from top to the top and measuring to the bottom. So these two, what I'm saying is, these two has the same thickness, and you're going to see that it will always cut this point, the origin. Okay, and then this is where the tension will be, positive stress at the bottom. Okay, this is how you draw your stress diagram. Okay, and the beautiful thing about this point, this axis, this point, this line, is that this is the center of gravity. Okay, that's the reason why you need to find the center of gravity for your beam. And then you can say that, okay, center of gravity is here, right? I will put this sigma axis on this location. Any point that is above, it is up here. Any point that is below, that is below here. Okay, and as you draw the two-dimensional cross section, on top is compression, negative stress, below is tension, positive stress. Okay, it will always form a straight line. Okay, so and it will always form a straight line. It will always intersect at the origin. So basically, the lines will always be like this, okay, or like this, or like this, or like this, depending on how much moment you create, okay, by the force. Okay. Going deeper into this, so this is how you look, right? So let's say now I have a T-shaped beam, and it's being pushed down, right? So when I push down, the beam will bend like this, and the top will have compression, the bottom will have tension, right? And then first thing you should do is to find the center of gravity, okay? Because at this point, the center of gravity, the beam is rotating about this axis, okay? The beam will be about this axis, which is this point here, okay? So how are you going to draw the stress diagram? Locate the CG, like how you do here, and then straight away you draw the stress axis, sigma. Okay, then you go and draw the y-axis, the height axis, y. Okay, so this one, this line always follow the position of the CG. Okay, and then you mark the limits of the shape. The limit means the highest point and the lowest point. Okay, so the highest point will be the top of the T, so which is here. The lowest point is bottom of the T, which is here. Okay. Straight away we know that at the center of gravity the stress will be 0. So this is the first point that you can plot. It will always cut here. Okay. Second, compression. So at the top, I'm having compression, right? So at this line, this y value here, y top, okay, the sigma will be negative. Okay, maybe let's say let's say it's here, okay, it's up to you to find out. So this value, this exact value, this is the sigma compression. Okay, you are going to find out using the formula my over I. Okay, and the y that you use is this y top. Okay, with reference from the CG. How far away is it? It's the top from the CG. This is the value that you need to put here. And then this moment is the moment that you find from this table. Okay, and the I, of course, you have to find the value of the I for this T shape. Okay, and you will be able to find this exact value. This, what compression is this? Okay, how much negative compression? Okay, and your stress line is going to join from here to here. It's going to be a straight line. Okay, so this is your stress line. Okay, apologies, I shouldn't extend past this point because below there's no beam, so there's no stress here. Okay, so it will only end here. Okay, and you see the moment I draw this, my line is basically fixed already. I don't even know, I don't even need to calculate to know that it is going to extend until I reach the bottom, right? And do you realize that when it hits the bottom, what does this point represent? This value here. This value here actually represents the amount of tension stress that the beam will get. So this is sigma tension. Okay. And if you look at it, the higher the y, okay, so the bigger the y, the bigger the stress. Okay, the top y is smaller than the bottom y, right? So the top will have a smaller stress value. The magnitude, not the sign. The magnitude is smaller than this magnitude, right? Okay, so for this case, the T shape, the higher stress value will be caused by the tension. Okay, the compression will actually have a smaller value. Okay, if you think about it, if now the beam is now an inverted T, okay, maybe we draw this lah. If your bending is now an inverted T, right? The beam is now an inverted T. Your CG will now be lower, right? And then you place your sigma axis here. You place your y axis here. The top will be here. The bottom will be here. Okay, so you see the bottom y is now smaller than the top y, right? And then if I draw the stress line, you see this stress, this value will be smaller than this value. Okay, so once the shape gets inverted, the higher stress is switched. Okay, and you always use this formula to find what is the exact amount of this stress. Okay, so if you want to find the bottom tension stress, right, is the same. Okay, sigma tension is equals to my over I. But now the y is this value, y bottom. Okay, you just need to take the magnitude. You don't need to put the sign. Okay, then you can find out already. Okay. Okay, now let's look at one example as an illustration. Let's look at tutorial question number 8.7. Okay, this is a T shape. This is a T shape beam. Okay, it is simply supported and it is experiencing a UDL. Okay, the beam is 4 meters long. The UDL is 5 kilonewton per meter. All right. So 5 kilonewton per meter UDL. Straight away, you should be able to use this diagram and find out how much moment is there. Okay, the highest moment will be at the center, and the value will be WL square over 8. So the W, you will use the value of 5. The L is 4 meters, which is 4 over here. Okay, later we will see. But first, let's find the CG first. Okay, I've already calculated. What you do is you split the T into 2 rectangles. The top horizontal rectangle, rectangle 1, and the bottom vertical rectangle, rectangle 2. Okay, you will have to measure from the top because the question says find the position of the centroid from the top edge, which is with reference to the top line. I need to find the CG of the rectangle 1, okay, which you can find out is half the thickness, which is 10. Okay, the CG of rectangle 2 is here. Okay, since the rectangle 2 is 280, right, so the middle should be 140, right, but then there's another 20 here, so y2 is 140 plus 20, okay, 160. So we need to find y bar. Okay, and this will be my GG line, center of gravity. So the T for this case is rotating about the GG line, okay, the axis. So from here you will find out that the y bar is 97.5 from the top. Okay, 97.5. And then you need to find the value of I. Okay, I, because the rectangle 1 and rectangle 2, they are centroids, right, have a distance away from the GG. So you need to include H, the distance offset of their respective CG. Okay, so H1 is this value here, this value, okay, 87.5. And H2 is the distance CG2 is away from the GG line, okay, which is 62.5. Okay, so it's basically this minus this, okay, and H1 is this minus this. Okay, then you sum up and you will be able to get total I is 89.22 times 10 to the power of 6 mm4. Okay, so having cleared these two, now you can go and find the stress. Okay, again, the top, you are going to place the axis, the sigma axis, at the GG. Okay, this is the GG, the center of gravity. You're going to place the sigma axis here. Okay, and then you're going to draw the y-axis, height. Okay, and the 2 points of the 2 limit, the top and the bottom, will be here and here. Okay, based on the height. So this is 97.5, and this height is how much? It's 300 minus 97.5. Okay, so this one would be okay, this is 97.5, this would be 202.5. okay, of course this is minus, but the sign doesn't matter so much, okay, for this topic. Okay, and then you know that it's undergoing a UDL, right? UDL. Okay, so the beam is going to bend this way. Okay, once you bend this way, you know that the top is having a compression and the bottom is having a tension. Okay, and so we can safely plot the stress line like this. It's always going to it's always going to go through the origin, right? So I can just draw a line like this. So this is my stress. Okay, this is the value of compression. This value here, what is this value? Okay, which you're going to find out. And this one, this value is the sigma tension. Okay, how much is this value tension existing at the base? Okay, so this is the line that you will draw. In order to use sigma equals to my over I, you need to find the moment first. Okay, so the moment for this case, I just now show you already, WL square over 8, which is a 5 times 4 square over 8. Okay, which is a 10 kilonewton meters. Okay, so let's find out. Stress compression at the top is how much? My over I. Okay, so this is 10. So this is the time we convert everything to SI units. So 10 kilonewton is 10,000 Newton meters. Okay, Y is 97.5 mm. So this is 0.0975 meters. Okay, meters. 1, 2, 3. Okay, so I would be just now you managed to find is 10 to mm to the power of 4, right? If I want to convert to mm to the power meter 4, I have to multiply 10 to the power of minus 12. Okay, so after conversion, it will be minus 6 meter 4. Okay, so let's put it over here. 89.22 times 10 to the power of minus 6. So once you use SI units for all the terms, the stress that you will derive will be in Pascal, also at SI unit. Okay, so let's find out what value is this. Okay, 10.928 times 10 to the power of 6 Pascal. Okay, 1, 2, 3, 4, 5, 6, which is 10.928 megapascal. This is your compression. Okay, So how do we find the tension? Also my over I. M is the same, 10,000. Y, this time Y is this height. Okay, is this height here. Okay, 202.5. Okay, which is 0.02025 meters. Okay, over 89.22. No, 0.202, 0.2, sorry, 0.2025. Okay, so this one is 10 to the power minus 6. Okay, you're gonna get 22.69 times 10 to the power of 6 Pascal. Okay, which is 22.7 megapascal. Okay, so this is how you do the calculation, and the answer to the question, what is the maximum stress? It will be comparing between these two. It will be the tension, 22.7 megapascal. Okay, and the maximum bending moment will be 10 kilonewton meters, and it will be at the center of the beam. Okay, center of the length of the beam. All right, so I hope you gain an understanding, although again this video is quite long. I have explained at length. Okay, yeah, all the best.